Hello, everyone. Thank you all for coming. Thanks for putting up with me in English as well. I'm going to talk about error handling tonight. Hopefully that was obvious from the title. The title is, of course, a bit of a play on words. And there's a few meanings you can read into it. But the picture in the background is from the Apollo 13 mission. It's actually a picture from the NASA control room during that mission. And as part of the preparation for this talk, I had to go and watch the film from the 90s about the Apollo 13 mission, because one of the quotes from that film, from the middle of it during the oxygen tank crisis, was, "Failure is not an option." It was actually coined in that film. He didn't say it in real life, but in the film he said that. Later he used that as the title for his autobiography, so I suppose he did say it in the end. And in that sense, that failure is not an option. Sometimes it is actually something we meet in our code, that something absolutely mustn't happen or should not happen. And we'll look at that a little bit more later. But the other play on words, and the reason I reversed it here, is because we now have the type optional in the language, or at least in the library. And some people do use that for error handling, or something that looks like error handling. So we're going to look a bit about that as well. In fact, we're going to look at the whole past, present, and future of error handling in C++ and weigh it all up. So to get started on that, I want to go right back to basics, and this isn't going to work, so I'll just use the keyboard. Ask, what is an error? Just, what's the essence of an error? What is it? What do we really mean when we talk about errors? Very vaguely, we could say, it's just when something went wrong. But the reason I put this on the screen is because it's actually part of a slightly larger picture that I got from Twitter a little while back. And I'm just going to zoom in on there. This is an error message that someone got from their banking app. And I think it's just worth reading that because it's absolutely amazing that an end user would receive this while using their banking app. What the best part, though, is I don't know if the person that tweeted this really understood what's going on there. I mean, we can read this and imagine it's probably some sort of Java backend, but the end user wouldn't have a hope. This is what the person that tweeted actually said, which I thought was quite amusing. So crafting good error messages is not really what this talk is about. How you actually surface errors maybe that is a bit, but just wanted to get this warmed up. Because not all errors and not all bugs, which are different things but they're related, they're not all as visible as this. And in fact, a lot of bugs go completely unnoticed, and it seems like we're getting away with them. If we don't actually see the result of a bug, is it really there? But actually, we know from hard-won experience that these are the worst types of bugs because they will show up sooner or later, typically in front of a customer or an end user, and possibly after having done loads of damage that you hadn't actually seen up until then. And they're really hard to track down. They're really hard to debug and diagnose. So these are the worst types of bugs, the ones we want to surface as soon as possible so that we can do something about them. So we're going to look a little bit about that as well. Before we get into that, I want to establish some other terminology. We often talk about the happy path. So we talked about the actual error condition in our code, but then there's some code that happens after that. So the happy path is what happens when no error occurred, of course, which raises the question, what do we call the path through the code when an error does occur? In other words, what's the opposite of the happy path? And if you ask someone that directly, their first instinct is maybe to say the sad path, which doesn't really work, and no one actually uses that in practice. Funnily enough, there doesn't seem to be much of a consensus on what the opposite of the happy path is. I did some research on this, and I did come across a tweet by Ron Jeffries, where he asked the same question. I didn't get much of a consensus in his replies, but I like some of the replies he got. Things like the veil of tears and the path of sorrow. None of them really work very well, so I think we'll just stick for the boring error path. It's about closest we can get to the opposite of the happy path. So that's the term we're going to use through this. So I mentioned, or sort of touched on already, there's different types of errors. In fact, there's lots of different types of errors. We meet them all the time. There's one I want to start with, which I'm sure you're very familiar with, and probably seen this a lot, the "this should never happen" error. We've probably put assertions like this in our code, and then it's blown up at some point, because although they shouldn't happen, they actually do. And there's a very good reason for that. But beautiful moment of irony, when I was first preparing this particular slide, Keynote crashed on me and gave me this stack dump, which I thought was absolutely perfect. And I really love the exception note there, xe corpse notify. Reminds me of the singleton bean factory exploding in the earlier example. So end users are not meant to see this, because really these represent bugs in the code, but they do happen. And we do need to have some way to handle these things. So let's break this down into a couple more categories. So we've got the should never happen category. I'm going to add to that shouldn't usually happen, and might happen, but we'd prefer it if it didn't. So what are we talking about here? Let's put some examples to this. So should never happen. These are the absolute hard errors, definitely bugs. Things like null dereference, out of range access, use after free, those sorts of things. I'm sure you can add a few more to that list. If they do happen, it's because of some bug that's occurred either at that point or earlier. Don't think we'll disagree with that. Now, the middle one is the interesting one. We're going to come back to this in a moment, but the example I'm going to put there is out of heap memory. And in fact, it's pretty much the only one that belongs in this bucket. You could argue there's a couple more as well, but they all have similar properties about them. But just to fill out the rest of the examples, the might happen, but prefer if we didn't. We've got things like file not found, couldn't convert from a string. Examples of things where this is what we wanted to happen, we couldn't do that, so we're going to do something else instead. We sort of treat the error more closely to control flow. We prefer that, but we can do this instead. And this is really the majority of errors that we have to deal with in our code. We obviously want to hope to minimize the top lot. So really we're talking about the bottom a lot when we're talking about error handling. But I think it's important to keep in mind the whole spectrum, because we can often get these things confused. So let's break these things down a different way. I mentioned that should never happen represents a bug, or in other words, a logic error. Whereas the bottom bucket is to do with I/O or side effects. And if you think about it, it's the only way it can be. The errors must either occur from something inside the code, the logic, a bug, or from outside the code. If it's coming from outside, it must be I/O. So that sort of makes sense, except there's a couple of little wrinkles to this. First one is that sometimes, that file really must be there. That string really must encode an integer or whatever it is. Those bottom category of errors may actually be logic errors depending on the context that they're being used in. And really, you can only decide that at the call site. And yet, we often implement our error handling strategy on the implementation side, mostly because of the tools that we currently have available to us. So that's a bit of a problem, and can lead to pessimizations or other problems. The other little wrinkle is that middle one. I said I'd get back to that, the out-of-heap memory. Because in terms of exceptions, we'll deal a bit more with exceptions later, but exceptions in C++, the one that can literally come from almost anywhere is bad alloc. And very often when we're trying to write exception-safe code, really this is what we're guarding against. And yet in most code bases, how prepared are we really to deal with being out of heap memory? In fact, I had a quote from Herb Sutter recently that if you see bad alloc, then that's a sign that you're not handling out of memory. Because virtually no one does it. They try to make exception-safe code, but handling bad alloc is actually a really specialized thing that you can do. And there are definitely some code bases that absolutely need to do it, and they do it. But handling bad alloc is typically not the way that that's done. And yet, we write all this code to try and handle it. So it's a real problem. It's a bit of an outlier. And there's been a recent call to say, well, maybe we shouldn't handle those with exceptions. And in fact, the proposal is that the default approach, when you ask for memory and you don't get it, is to just terminate at that point. So the default, you can still get exceptions or hand it another way. For example, we have the no-throwing version of new already that we can use. And there are proposals to make that choice a bit richer. But the point is, most code shouldn't have to worry about this because currently it's not really handling it anyway, and it's just complicating code unnecessarily. So there's a case for that. So another way to look at these categories is that The sort of the I/O bucket down the bottom represent recoverable errors. We can actually carry on afterwards. We sort of anticipate what this might happen. We'll do something else instead. Whereas logic errors are not recoverable. And it sort of sounds obvious when you think about it, and yet a lot of code does try to handle logic errors. In fact, we have stood logic error in the standard. And it's been said that stood logic error is itself a logic error, because we shouldn't be throwing exceptions for logic errors. We should be treating them more like a contract. And in fact, I would say that that top section should be handled with contracts. And what I mean by that is code that will test the condition and will terminate at that point. Or maybe having assumed that we'll never get into that situation, leave it to undefined behavior. Of course, there's a dangerous area, but there's definitely cases where that's appropriate. So in general, we talk about contracts. Currently in C++, the only mechanism we have in the standard for this is the assert statement, which will get you so far. We should definitely be using asserts more than we do, I think. But they're a bit limited. They're not very fine-grained. They certainly have some problems. So we'll talk about the proposal for contracts in just a moment. Come back to that. As I say, there's a proposal for treating heap memory specially and actually terminate or possibly offer you more choices with error returns. And then the bottom category is where we usually use exceptions or, again, error returns. So we're going to spend most of the time talking about that bottom category, but just wanted to come back to that contracts point because there is a proposal that has recently, I think it was actually not the last meeting, but the one before that, been accepted into the standard for C++ 20 for support for contract-based programming C++. So that's in C++ 20. It's still being discussed in San Diego. It's still being refined. So there's still a chance to actually make it even better. But this will give you much more fine-grained control, much more ability to customize what happens when a contract fails, different types of contracts, and they are expressed in attributes rather than macros, which also make them visible to the compiler, and in some cases things can be checked at compile time. So if you haven't looked at this already, definitely recommend you do it. We're not going to dig into it anymore in this talk. There are other talks specifically about contracts that I encourage you to see, because I think this is going to change the way that we approach our code, at least once we get C++ 20. So I said that we're going to spend most of the time talking about recoverable errors, so let's go there. And the way I want to do this is by looking at the different approaches that we have and weighing them up or scoring them, and then seeing what the trade-offs are, and whether there's one that's better than another, or where we can go from there. So I'm going to keep a little scorecard. Each score is going to be a number between 1 and 10, where 10 is good, 1 is bad. So starting with the overhead of the error handling strategy. So typically performance, but that can also be image size overhead, and also whether it's deterministic or not. There's some domains that actually matters more than the raw performance. And just scoring the overhead itself is not enough. We actually need to split it up between the happy path and the error path, because they may be different and that may have different consequences. But I also want to look at the safety of the approach. How safe is it to use, or how hard is it to use and easy to misuse? So I think that's also important. The noise, so how much noise it introduces into your code as opposed to not handling an error. So again, some of these are a little bit inverted. So when I talk about noise, a high score is actually good. And a high score for overhead is good, so apologies for that. But a lot of error handling approaches, because they use normal control flow, they get very noisy. We'll look at that. And closely related to that, and I have separated it out, but maybe we should just bundle this in with noise, is whether you have a separate path for the error path and the happy path, which again can lead to noisier code otherwise. And then reasonability, I think, is often overlooked. Really important. How hard or easy it is to reason about the error handling properties of your code. Does a piece of code emit errors or not? How do you handle them? That sort of thing. And then composability. And really this is two things. This is the composability of the error handling itself, but also how much the error handling approach interferes with the composability of the code without the error handling. You know, can you compose functions together, or is the error handling getting in the way? That sort of thing. And then finally, message is just how much extra information you can convey about the error. Or is it just whether an error occurred? So that's scores I'm going to use. And we're going to look at some different error handling approaches and weigh them up, starting with error codes, a few variations thereof. And we're going to use this example for most of these, which is a function which creates a directory in the file system. Or at least that's what it purports to do. So it takes a string, and in the first example returns a Boolean. And although that doesn't actually explicitly say that the Boolean says whether it works or not, just by convention, we'll look at that, and that's what we will assume, given no other information. Usually a function that returns a ball that's not a predicate probably means it's the status of the function. So I'm reasonably happy to say that that's what we would call marked propagation. So we can actually see in the signature of the function that an error may occur. The usage code is not surprising, I'm sure. So just a normal if statement against control flow here. In this simple example, the happy path and the error path appear to be separate. But of course, if you then follow on, more steps on the happy path are going to be nested, unless you sort of invert it with early returns, but you can't always do that. So let's have a look at the score. So first thing to note is that the overhead scores are very high, as in low overhead. It's good. It's not quite a 10 because there is some overhead, but it's pretty minimal. And that's both on the happy path and the error path, importantly. And I should say these scores, these are just ones I plucked out of the air from sort of thinking it through. Nothing particularly scientific about this. And as I've done different versions of this talk, I have tweaked them. So if you disagree with the actual, the specific scores, don't worry too much. It's the overall direction that I'm interested in here. So safety is pretty low here, I think, because it's actually really easy to misuse this. It's really easy to ignore the error condition and maybe carry on assuming it's worked. So I'll put safety down. It's also quite noisy because you're mixing control flow with error handling. And again, for the separate paths, that's the same. But reasonability is actually not bad. Again, because we can, by convention, infer that Boolean indicates whether an error occurred, we can reason about that code, especially if we see the if statement in there. But composability suffers because we're using the return channel, the return type, for the error handling. We can't use it for anything else, so it gets in the way of composability. And of course, there's no additional information being conveyed, so the message score is low. So I've gone through those one by one here, because it's the first one. I'm just going to concentrate on the differences now. Let's see what we can do to fix this a bit. So you may be thinking, well, we can make this a bit safer by putting no discard on there. That's the attribute introduced in C++ 17, which doesn't guarantee, but it gives the compiler the ability to warn you if you don't immediately use that return value, and most do. So I definitely recommend using that if you're going to use this type of approach. That will make it safer. Doesn't really affect any of the other scores, but that's definitely a small win, so that's good.
Noise increased.
You say the noise increased. I suppose because you've got the attribute there, yes. The noise score, I'm really more thinking about the usage code, but you're right though. Maybe we should dock 1 point on the noise. Good point. Another adjustment I've got to make. We can improve the message score by using a different return type. Using an integer here, that could equally be an enum or even a richer type. But assuming it's some integer type, I'm giving it a halfway score. So that's an improvement, but again, it makes it a little bit noisier in the usage code because now we've got to separately capture the result and then test it in a separate step. But it gives us another advantage. I particularly picked the example of creating a directory because one condition you can have when you create a directory is it already exists. And depending on how that's implemented, that may be conveyed via an error code. It often is, but in fact, it's not really an error in terms of the way you're using it. So now we can capture both cases and put them both on the happy path. So That's one advantage. So that's error returns, but another convention is to pass our error codes in as out parameters, usually by reference in C++, maybe by pointer as well. So otherwise, basically the same, except that now we're passing it in. So I'm still counting this as marked propagation because you can still see it in the signature, but I have put the reasonability score down a bit because it's not quite so obvious by convention that that's what's happening. It's a little bit more buried in the signature. I'll put the safety down a bit as well for the same reason, because it's a bit harder to use this correctly. But it does free up the return channel now. So now we can compose our functions more nicely, and we can also potentially reuse the error code value if you're sequencing several functions with the same approach. So yeah, some scores are going up, some are going down. This is the trend. Then we can start mixing some of these approaches as well. And this is actually what we tend to see more in real-world code. So mixing an error code passed in as an out parameter with a Boolean return. So we get the course, did an error occur on the return value, which we can use no discard to avoid us ignoring. Makes that easier. But then we can get the richer error through the code that we pass in. So a bit safer to use. It's a bit easier to reason about now because we have the Boolean there. But again, we lose our composability. So it's still all trade-offs. So maybe we try a completely different approach and we just remove the error handling from the signature altogether. Just store it in a global variable, or probably these days a thread local variable. Now this makes it unmarked. There's nothing in the signature that tells us that this may fail in some way. So that definitely affects the safety. It's right down. But it does clean things up a bit. So the noise score is raised a bit. And the composability is a bit better because we can compose functions freely, although it's a bit vague whether you can compose the error handling itself. In fact, sometimes that you can lose one error code just by calling another function. So definitely trade-offs, but I think the fact that this is unmarked is really a big problem. And in fact, most people would look at this and say, oh, I'd never do that. So what we often do is mix these approaches. Again, this is quite a common error handling strategy, to have the actual error code giving you richer information stored globally or thread locally, but just a Boolean return to tell you that something happened, and then you need to go and look at it. So a bit safer, I agree, still not a perfect score. Slightly easier to reason about as well. But again, we lost that composability because now we're using the return value again. So we're still not quite getting there. So there's definitely different problems with error codes, different trade-offs we can make. None of them are perfect. I didn't even mention the overhead goes up with this version because now we're probably going to be using thread local storage, which has a cost. So this is the state we were in 20, 25 years ago. We decided as a community that we need to do better. So we came up with a system that we called exceptions. So it must be better. This addresses all the problems, doesn't it? Well, let's just recap what exceptions are. I'm not going to go into detail, but first thing to note is it's unmarked, which we just said was really bad. And yet that's what we live with today. There's nothing in the signature to suggest that this does throw an exception. Now we do have noexcept now that tells us that it won't throw an exception, but the absence of that doesn't guarantee that that it does throw. So I'd still class this as unmarked. Usage code is familiar, I'm sure, so I won't go into that. Just have a look straight at the scores. And the overhead on the happy path is really good. That's what it's optimized for. But the overhead on the error path is abysmal. And in fact, this score between 1 and 10 doesn't really capture it. Maybe more like a 0.1. And we'll get into some more figures in a minute. But it really is bad because we've been telling ourselves all these years, well, we only use exceptions in exceptional circumstances where we don't really care about the performance anymore. We want to optimize just the happy path. But what we've been finding is that that's not really very satisfactory for a lot of cases, but some domains it actually makes it impossible to use this altogether. And we'll talk about that a bit more in a moment as well. But I want to get through the other scores because it is safer. Because now you are forced to deal with it. At least at runtime, if you forget to do a try-catch, you will find out exactly where that happened to some degree. And the noise is less. And the separate path score is perfect because we have completely separated the error handling from the normal control flow. Got a nice separation of paths. And as a result, it's also very composable. Doesn't interfere with the composability of the functions. And the error handling itself is composable. You can have throws across multiple stack frames. You can have try-catches and across different stack frames as well. Converting errors, however you want to compose them, you can do it. So there's a lot going for exceptions, but there's a couple of big problems. Overhead on the error path, and the safety because of the unmarked propagation. And I've put reasonability down as well, again, because it's unmarked. So they're the big problems of exceptions. Just for completeness, I thought I'd mention the directory already exists case. Naively, we would have to deal with it this way. Of course, we wouldn't do that in practice. So it's not really, it's a bit of a non-issue, but it is something else you have to think about. These are different to error codes. So I said I'd look at some numbers, and unfortunately we don't have any real, what you might call scientific numbers to look at. We've got lots of different people's own sort of benchmarks that all give different variations on the same theme. This is one I stole from Niall Douglas, who's been working on stood expected and boost outcome. And here he's comparing the cost of returning an error up 10 stack frames on the x64 architecture. Lots of different compilers. And there's actually 4 colored bars there. May not be very clear, but the yellow one is the exceptions, and the others are different types of error returns. What's interesting is the y-axis is exponential. So the cost of returning an error up 10 stack frames is at least 2 orders of magnitude more expensive than error returns, which is really sort of tells you everything you need to know. Again, you can quibble with exactly what this represents, but everyone seems to be coming up with very similar stories that the cost of exceptions on the error path is just unbearably high. And for cases that matters, all bets are off. In fact, the 2018 C++ Foundation Developer Survey reported that 52% of C++ developers, so more than half, reported that exceptions were banned in part or all of their project code. And what's even more remarkable is what it continues in this quote, i.e. most are not allowed to freely use C++'s primary recommended error handling model that's required to use the C++ standard language and library. In a lot of domains, people are having to use a non-standard fork of the standard library effectively, because you can't actually use the standard library without exceptions, as specified. More than half of C++ developers are in this situation at least some of the time. And I think that's really damning. It really says that there's a problem here that we need to deal with. So clearly, we need to look beyond exceptions. Error codes definitely had their problems as well. We saw that. So what else can we do? You've probably heard a lot of talk lately about ADT-based error handling. So let's have a look at that. What does it stand for, first of all? Algebraic data types. So if you're not already familiar with algebraic data types, we don't really need to know all the details. They consist of product types and sum types. And actually, it's sum types that we're interested here when it comes to error handling. Product types are really interesting as well, but for error handling, we're only really talking about sum types. Really, it should be sum type-oriented error handling. And we've got 2 types in the language now, as a C++ 17, optional and variant. And we've got stood expected being proposed for 20. And there's a few others possibly coming in the pipeline as well. We've got boost outcome, Lots of people have rolled their own. There's a general pattern here. That's what we're really going to be looking at. So what actually is it? Let's have a look at an example. So here's an example of a prototypical date class. You can see it's got a constructor that's doing some validation, incomplete, but don't worry about that. And we're doing a more sort of contract-oriented approach here. So we're saying we're just relying on you providing valid data. So maybe we want to wrap this in something that actually does that validation more speculatively. Something where you wouldn't want to pay the cost of exceptions, certainly. So we might do something like this. Here I've just added a static method called make. So it's actually like a factory function. So that does the validation in an if statement, and will return an empty optional if it fails, otherwise returns the actual constructed date wrapped in an optional. So we get an optional date. And then in the usage code, we can just compare that in an if statement because it has an explicit conversion to bool. And if it is valid, we can dereference it like a pointer. Otherwise, well, we don't get any more information than that, so we just have to report that there's an error. So we're back to control flow, but we've got some different trade-offs. We'll have a look at the scores in a moment. Just for completeness, if you do start writing factory methods like this that will forward on to something that actually has undefined behavior, I do recommend that if you want to expose the undefined behavior version, that you make that very explicit in the code. So I typically use something like the unchecked suffix, but that's orthogonal to what we're talking about, so I'll move on. Where's the scores? Here they are. So the overhead is comparable to error codes. I've put it slightly lower, 8s instead of 9s, and depending on the compiler, that may actually optimize back to what we had before. So I'm being a bit conservative there. But I think the safety is pretty good because we're pretty much confronted with the optional. We have to deal with it. You can dereference it without checking, but you do have to work a bit more to do that. So it's not a perfect safety score, but it's pretty good. And it's fairly expressive in terms of the intention. But it does make the code more noisy. We've got more types involved. We're still back to control flow-based error handling. So again, if you start nesting this, it gets messy. We've got no separation of paths. But again, for the same reason as the safety, it's much easier to reason about. That the types are actually telling you more about what's going on, what to expect. As I said, with optional, we're not saying what the error was, only that it occurred, so we've got a low message score. So, again, different trade-offs, much more similar to some of the error code returns. But we've got a starting point here. There's more we can do. So addressing the message, first of all, because optional just tells us we've got a value or not. If we went with stood variant, now we could say, well, it's either a date or something else. Just for the example here, I've used a string. You would probably use a more custom error type, but just makes it easier on the slide. So now we can say, we can give different strings depending on what the failure actually was. Obviously, this example is a little bit contrived. And in the usage code, we can ask it whether it holds alternative, i.e. has a particular type in there. If holds alternative date, then we follow the happy path. And then we can use stood get to actually get the date out, or stood get to get the string out in the case of an error. So we can do all of that, but I have to admit, it's pretty ugly. I wouldn't do this in practice, but let's just have a look at the scores. So we can see that safety is down a bit. It's going to take a hit just because it's harder to use, I think, because there's just so much syntax in there. Definitely very noisy. I put the lowest possible score for that. No separation paths because we haven't solved the control flow issue, but we do get our message score up a bit. In fact, we've got a perfect score for message. We can put whatever type we like in there. So there's something here, but we're trading off again. In fact, the big problem with this is that stood variant is not really the right type. It's not expressive enough for what we need. The syntax is getting in the way. Or I should say that there is an alternative form. If you stood get if, it will convert it effectively to an optional, so we can improve the syntax a bit there. But I still think we can do better. So I'm going to jump on to the stood expected proposal. So this is still at the proposal stage. I think it's being received favourably by the committee, but hasn't actually been accepted in yet, but there's still a chance that we'll get in for 20. What is it? It's very much like a customised version of stood variant, just for use with error handling, and just for the case we have either a type or an error. So it looks very similar in the return type. We have a stood expected of date, or in this case stood string. Again, we can use any type we want there. We use stood make unexpected for the error case, and then just return the valid date otherwise. But in the usage, I think this is much cleaner. Now we've got the explicit conversion to bool for the if statement. We can dereference again like optional, like a pointer in the happy path case. And in the error path, we can call .error. It's much more descriptive. It's much easier to reason about what's going on. In fact, let's have a look at those scores. So reasonability is fine. It's less noisy than variant. It's still not perfect by any stretch. And it's a bit safer because it's much easier to use. It's easy to see what's going on and what you expect. But we've still got quite a big mix of numbers here. And we're starting to get to the leading edge of where we're going with error handling in C++ at the moment. Is this really what we're heading for? Just a different set of trade-offs? Can we do better than this? Well, talked a lot about composability and the problem with the happy path and nesting. So let's start looking at some examples with more than one function involved to see where we go next. So for this example, I'm going to use two functions. Function that's going to convert a string to an integer, but it's going to return a stood expected, so if it couldn't convert it, it gives you an error string instead. And then divide, which takes two integers, and again, returns a stood expected. So if it's going to divide by 0, that will give you an error there. And what we want to do is compose these two things together. So we can't just return the result of toInt and pass it into divide because we've got a stood expected. So this is the sort of code you might write to use it. So convert the string to an integer, we get a result, test the result. If it's an error, we report that. Otherwise, we carry on in a separate block and call divide by dereferencing that. And again, this is the nicer syntax we stood expected. Got a lot of nesting here, a lot of noise. In fact, to see how bad this is, all the code that's highlighted is the happy path. And all the rest of the code around it is the error handling boilerplate. So we're definitely quite a long way off from being there yet. So what can we do about this? Well, a year or so ago, Simon Brand wrote this blog post, Functional Exceptionless Error Handling with Optional and Expected. So invoking functional programming. In fact, functional programming languages have types like this, like optional and variant, as their bread and butter. They've had ways of dealing with this for years. So let's see what we can learn from them. Now in this post, he proposes adding some methods to optional and expected. There's two methods, and then, and map. I've got some examples there, but I'll show you some different examples in a moment. First of all, just to note that in San Diego, by the way, this is a beach in San Diego, this was actually proposed for inclusion in the standard, so not just a blog post anymore. This is being received quite favourably, it's being progressed along. So far, just the monadic operations for still optional, but there's a follow-up for expected. So I've crept the monadic word in there. We'll look at that in a moment. But we can do the same thing even today with optional and expected, just by writing some helper functions. And those two methods that Simon mentioned, and then and map, I've actually wrapped them into a single one here, which is what's responsible for that boilerplate at the top. That's just some templatey stuff to take a return type, and if it's already an expected, give you that. Otherwise, it's going to wrap it in expected. If you follow it through, there's not much more to it than that. That just means that this function can compose things either that already return an expected or that don't. So it's playing both of those roles. So I've called this with. It takes an expected. It's fully generic, so it can take any expected with any error type. And also a lambda function. And that lambda function is going to call with the dereferenced option or expected, sorry, if it has a value. Otherwise, it effectively forwards on the error. It has to rewrap it in a new expected because it may be a different expected type. But that's really all it's doing. So either forwarding on to the lambda or passing back the unexpected. Pretty simple, but this represents the bit that was causing all the noise. So let's see how that improves things. So this is the same example, now using our with helper. So we can see highlighted code is where we start. So it's our first call to toInt. And if that actually has a value, then the with helper is going to call the lambda immediately below it with the dereferenced value. So we haven't had to do the error checking ourselves. We either get called or we don't. So now we can use that safely. And that's passing on to the second function, divide, with that value, which again returns an expected. So the second with helper will then call the second lambda in that case. Again, we've got no if statements in here. They're all in the helper function. So not really actually much of an improvement on the face of it. But let's have a look at the scores. I think it is safer because we have removed most of the moving parts and we're not having to do the dereferencing ourselves. That's done for us. But it's still pretty noisy. We are starting to see separate paths emerging though, because now most of this is at the happy path and the error handling has been shunted off to the end. So it's got something going for it. But it's got a good composability score because that's basically how this is working. Everything is composing. So the scores are creeping up, but I still don't like this. And the big problem with this is that C++ doesn't really do functional composition very well. So a functional programming language, functional composition is its bread and butter. It's optimized for that in the syntax. C++ isn't. That's why it's all inside out. But we can fake it, and one way we can do that is to rename our helper function into an operator, specifically an infix operator. I've used the pipe operator because that seems to be how these things are normally done. That's the only change I'm making here. But see how this affects the example code. So now, the logic flows the right way. We've got our first call at the top. The value from that gets passed on to the second lambda. Value from that gets passed on to the third lambda. It's a lot tidier. It's a lot more logical. There is still some error handling boilerplate mixed in there, though, mostly because of the lambda syntax, unfortunately. But I think this is definitely an improvement if you can bear to live with the operator syntax. So how does that score? Well, I will lower the noise, or improve the noise score. Like I say, it's still a bit noisy. And composability, actually that was already up, that's a typo. So it's really just the noise score. So the numbers are getting better. And this really does seem to be as far as we can go in the language as it is today. Some people are embracing this, others not. But I don't think you can argue with this. Well, you can argue with the scores. We'll do that afterwards. But I don't think you can argue with the direction of the scores, at least. But we mentioned functional programming languages, how they've been doing this for years. Maybe they got some more tricks up their sleeves that we can learn from. So let's take it all the way to the top. Let's go to Haskell. So Haskell has this thing called do notation. And maybe you've heard of this, maybe you haven't. But it doesn't actually take a lot to explain, at least enough to get us through here. It says on the Haskell wiki that it's syntactic sugar for use with monadic expressions. And that's really what we've been dealing with. It's been a monadic expression. We've got a bind and a map. That's how this has all been pieced together. You don't actually need to know how that works to make use of it. But our pipe operator, as I say, there's really two forms, is taking the place of the, no, that's not going to work. The operators you can see at the bottom there, the greater than, and the greater than equals. One of those is map, one of those is bind. And what's happening is in the do notation, every time you see the semicolon, it's not like a semicolon in C++, it's actually converting that effectively to, or transforming it to one of those other operators. So you've got something that looks very imperative that's been sort of resequenced as a set of expressions in lambdas that all get composed together. It's rewriting it for us. It'd be nice to have something like that in C++, I think. Now if we did, if we could wave a magic wand and get this in the language, what would it look like? Well, let's try and walk through this step by step and see where it might go, see whether it's something we might want to pursue. So here's the example we were looking at. This is like as good as we can get with our operator syntax. So we're not going to be introducing any new features or structures. We're really just going to introduce some syntactic sugar to map back to this. So imagine we're going to use a do keyword. So we'll set aside for the moment that do already has a meaning in C++, and that semicolons already have a meaning in C++. Just put those in there. So now when you put it in the do block, every time you see the semicolon, that's going to get mapped back to our pipe operator and then wrap the expression in a lambda. So that's all that means. So that's the first step. So let's deal with these semicolons first of all. You may have heard the term programmable semicolons. That's really what it's talking about here, because that's what's mapping to our operator. Well, we can do that with a keyword instead. Since this is error handling, let's use the try keyword. So now we get our C++ semicolons back, so I'll put those back in there. Now, notice that some of the happy path is still stuck at the bottom in the final if statement. Let's try and move that up as well. So we put that in the do block, and then we'll add a method on the return of the do called catch that takes a lambda that it passes the error onto in the case of an error. So now we've got our separation of happy path and error path. Remember, this still maps back to what we were looking at before with the lambdas. One step at a time. We've still got the do keyword there. I think we can complete that symmetry by using a try keyword instead. Now this now has to be a contextual keyword because try already has a meaning in C++ in this position. But in a function where you're using this syntax, we're waving our hands a bit here for a moment, try means this type of try, which is the one that mechanically translates back to our monadic error handling. What about the call site, the callee? So this is what we had, function returning a stood expected. Again, if we're just going to get the compiler to add some syntactic sugar, let's just say that every time you see throws, it will translate it back to a return of stood expected, or whatever we're returning. And similarly with that first return statement there that returns make unexpected, just put the throw keyword in there. Now this is where we get our context from. Any function marked throws means that the throw keyword, as well as the try keyword, have these new meanings. And in fact, if we've got that, we may as well just use the catch keyword as well, instead of our method name. And now we have something that looks pretty similar to our current exception syntax. But we can see by tracing it back that it's actually working more like the stood expected returns. And in fact, it has all of the same performance profiles as that. In fact, it has a few other properties as well. Some differences to current exceptions. It's now marked propagation. We can see in the signature that this is a function that may throw. And because we use the try keyword before the expression, we can see every line of code that may emit an error. So we're not hiding invisible control flow away in the code anymore. And that can be checked by the compiler. That try keyword before the two expressions don't strictly have to be there. It's really a documentation keyword for us. So we don't actually have to have that. Let's have a look at the scores. Okay, I'm biased. But, well, I can tell you that the overhead is going to be about as good as it gets, because we're just seeing that it translates back to something like error returns or set expected returns. And in fact, it's even better than that, because if you bake this in to the language, to the compiler, that it can do even more optimization, because it knows exactly why you're trying to do this. So, in fact, I put 9s here, might even go to a 10, depending on how conservative you want to be. Safety is about as good as it gets as well. We've got all the plus sides of exception handling, plus the marked propagation. We've got the nice clear separation of happy path and error path, so those scores are up as well. Same with reasonability, we now again benefit from the marked propagation. Composability is again is perfect, same as current exceptions, but now with these new semantics. And again, message, we can put any type in there that we want. So it's almost 10s across the board, 9s and 10s. So it'd be really nice if we could wave our magic wand and get something like this. But it's not just a thought experiment. There is a real proposal behind this, and you may have already heard about this now. This is being proposed by Herb Sutter. It's called Zero Overhead Deterministic Exceptions, Throwing Values. And I've only just sort of scratched the surface a bit of what's in there, tried to build up the rationale for it and how it comes together, but there's quite a few more bits and pieces to it. It's P0709, and I've got R1 on here. There's an R2 now. And if you go to the link at the top, though, you'll always get the latest version. And this has not been discussed at length in the committee yet, so it is early stages. But it's been very well received by SG14 and a lot of other people. And it's probably going to start discussing it more in Hawaii next year. A few more points to add that I didn't really cover. We're talking about throwing values. So there's no heap allocation involved, which is one of the big costs in dynamic exceptions. And there's also there's no RTTI involved in matching the exceptions, because again, they are just values which can be compared with an integer. Although we map this back to the monadic binding syntax with stood expected, you can actually use this syntax with constructors and operators. So it's better than error returns and stood expected than that. The value type is no more than 2 pointers in size, so it's a very efficient return. And there's actually a path for interoperating these new static exceptions with our current dynamic exceptions, so we don't have to throw them all away and start again. We can migrate piecemeal. And when you put this together with those points we talked about early on, moving a lot of stuff into contracts that really belong there, and treating heap allocation as a separate thing altogether, what's left fits really nicely into static exceptions. We could actually end up with something that will unify all of those people who are not doing standard C++ now, get everyone using new exceptions. So that's the end of the main part of the talk. If the pizza hasn't arrived yet, I've got a couple more bits to show as well, because there's a couple of other papers as well that the main one depends on. Status code and stood error is one. So that talks about the type that would actually be thrown in these exceptions, and in particular how that can be made so efficient that it can often go just in registers. And related to that is move relocates, which talks about the trivially relocatability of that type a way to express it so that you can just copy the bits for a move operation. And there's a parallel paper to that. In fact, I think I've got that here as well. Object relocation in terms of move plus destroy. We could go with either of those papers. This one's a bit more ambitious. Would be really nice for lots of reasons, but would make static exceptions get up to that 10 score, I think. About as good as it gets, if we can get something like this in the language as well. Now, all of those papers, and a lot more, I've put in the references that I've got on my website, in the top corner there, levelofindiraction.com/refs/cpp-optional.html. Or you can always find me on Twitter to ask me about that. So there's like a couple of pages full of references that I advise you to familiarize yourself with at least some of, because this is really going to change the shape of C++ in the next couple of releases. So that is the actual end of my talk. So thank you very much.